once we define magnetic flux, we can go back to the to Faraday's original discovery, and that had to do with that primary coil, the secondary coil, and the iron core. What came out of that is what's called Faraday's law of induction, and it quantifies how that magnetic field induces a current in that secondary circuit, or how it induces an EMF. So the EMF in that secondary circuit, as it turns out, it looks like, the formula for it looks like this. We have minus n delta phi over t. In actuality, it's a derivative. It's a d phi by dt. But we're only going to be dealing with things whose rate of change is constant, so the delta phi over t will work out just fine for us. The negative out front means that this EMF opposes the change in flux. And we'll talk more about how that works, but remember that a current generates a magnetic field. And so whatever direction this change in flux is, the induced current is going to flow in the direction that produces a B field that is in the opposite direction of this change in flux. Okay. But this gives the EMF, and then the current in the secondary circuit you could find by find based on what circuit elements or properties of the wire that are in that secondary circuit. Now there are a bunch of different applications of Faraday's law. Quite a few. There are a lot of electronic devices that use this. Perhaps the simplest is what's called a dynamic microphone, which has a diaphragm on it that just vibrates in accordance with the sound waves. And that oscillation moves a coil of wire that is wrapped around a magnet, and because it's moving over the magnet, the flux is changing, and so an EMF is induced in the coil. And through that current in the coil, the oscillations are amplified, and everyone hears the sound going through the sound system. The same sort of idea is used in a seismograph, which takes little tremors that happen before earthquakes, and during earthquakes, bigger tremors, and it causes something to vibrate, and again, that moves a coil on a magnet, and that current is interpreted by the seismograph. An electric guitar works in a similar way. There's a magnet on the pickup of an electric guitar, and it's a pretty strong magnet. So then, you've got the string of the guitar is, sitting here, and this pickup is right here, and it's a pretty strong magnet, which causes this string to become slightly magnetized. It induces magnetism in the string. And so then as that string moves closer to and further away from the coil, that, creates an EMF in that coil, which is, sent to an amplifier, and, it creates the sound that we know from. That's electric guitar. Did I say electric guitar? I think I did. Anyway. Any sort of electronic storage of information utilizes this principle as well. Computers, ATMs, credit card readers, all of these store information magnetically, so that when they're brought near, the magnetic storage is brought near a coil, and that changing flux allows the coil to, the coil sends a signal to the electronics that, it interprets as being the right ATM card, or being the credit card, who the credit card belongs to, or in the case of a computer, it pulls that data back off the hard drive. Another very sort of neat application that I hadn't heard of before was what's called a T-coil. And this is something that's used in hearing aids. On a telephone, apparently there's, as the speaker on a telephone does its thing, producing a sound, there's this magnetic field that is generated as the speaker, oscillates. And that wasn't planned, it just sort of is how the speaker works. But they use that in hearing aids that have this coil of wire. Then that coil picks up the vibration as well and is able to then produce extra sound that helps amplify what the speaker is doing. So it's not just taking the sound and making it louder. It's also picking up this magnetic vibration and using that to reinforce the sound that's being generated. Whereas if you just if you just make it louder, it's often not as clear as it is as a hearing aid that uses this T-coil. And many large gathering places are apparently using this, like churches and auditoriums and whatnot. So they put a loop of wire on the floor of the room, and so then the signal from the microphone is sent to that coil as well, and so then that coil generates a magnetic field that the T-coil in the hearing aid is able to pick up. And so depending on the venue, it may be that someone with a hearing aid could hear the speaker better than anybody else because of that T-coil. Anyway, so that's just some different applications of Faraday's law, and it's something that's very, very much in use in a lot of devices that we see every day. There's another law that's kind of related to Faraday's law. It's called Lenz's law, which is kind of what I already said, that the EMF opposes a change in flux. But I guess this result is important enough that this guy Lenz gets to name it himself. An induced current always flows in a direction that opposes the change that caused it. So we're going to look at how this plays out qualitatively. So let's say that we have a current loop here, and we're going to say it's perpendicular to the plane of the page. So if we looked at it, we would actually just see a straight line, but I'm going to kind of draw it so you can tell it's a loop, and it looks like, like this. Okay. And you take a magnet, and you start bringing it close to the coil. Now, as you bring this north pole closer, well, that means that the B field strength is greatest right by the north pole. So as we bring this closer, that means that our magnetic flux is increasing. The rate of change of the flux is positive, and it's increasing in the direction to the right. So there is the flux is increasing to the right. Okay? Because it's increasing to the right, the current generated in this loop opposes that change. Okay? So now let's look at our loop. Let's turn our loop sideways just so I can draw better with it. Here's our loop, and we're going to say that the magnet's moving into the page. Okay? Same situation, but I'm just rotating it so I can draw better. So that there's an increasing magnetic field into the page. Flux increasing into the page. Okay? Because that flux is increasing into the page, the induced current in this loop opposes that change. So flux into the page, the current wants to oppose that, so it'll generate a B field that would point out of the page, which means that current is flowing around this way. The induced current will flow, counterclockwise. Okay, because the flux is increasing into the page, and Lenz's law says that the current opposes that change, so it generates a B field coming out of the page. Okay. another way of thinking about it is that this wire is trying to repel the magnet. That is another way of thinking about opposing the change. So it's bringing its north here. Now remember, there's a B field generated by a wire that acts kind of like a bar magnet. And so it would act as though it was kind of like this, with a north-south here, which means that the B field, again, is flowing that way, or in this case, flowing out of the page, which means that the current is going up out of the page, or the B field is going out of the page, which means the current is flowing counterclockwise. So that's another way of thinking about it, is in terms of, if you look at the loop as a bar magnet, you know, how would you get a north that's going to repel it? This situation that I've drawn here is exactly the same as if our magnet was facing the other direction and we were moving it away. Okay, you're moving a south away, that means that the flux would still be increasing to the right, because a south brought really close would cause flux to the left, but if you're moving the magnet away, then you're decreasing that flux to the left, which means that your change in flux is to the right. And that gets kind of sticky to think about. It hurts your brain a little bit. So let's consider what would happen. Let's say we've got a north, south, and we're moving the south end toward this loop. Moving the south toward the loop. Again, pretend the loop is in the plane of the page. As we move this south toward the loop, this is a good point for you to pause the video and see if you can decide what direction the current is, and then you can unpause it and see if you're right. And I'll talk about it both ways. So south moving toward the loop, that means that the flux is doing what? Well, as we move this south closer, the magnetic field is stronger, but it's pointing toward the south. This is the velocity. The magnetic field is pointing toward that south pole. So as we move it, the flux is increasing to the left. There's more flux pointing through the loop toward the left. So the direction of increasing flux then is the opposite direction it was before. Out of the page, if I draw it sideways, is the direction of increasing flux. That doesn't look like increasing, but you heard me say it, so huzzah. The direction of increasing flux is out of the page, and since the direction of increasing flux is out of the page, the loop will generate a B field that will oppose that, which means we want to generate a B field that's pointing into the page, and so we put our thumb into the page and curl our fingers around, and we get a B field pointing in the opposite direction. A current pointing in the opposite direction, which generates a B field in the opposite direction. Okay, and this is the same as if we took a magnet oriented the opposite direction and moved it away from the loop.